The research proposes a novel active learning strategy, structured neural depth search, SNDS, which utilizes structured variational inference to optimize neural architecture depth during active learning. This approach addresses the inefficiency of traditional active learning methods by dynamically adjusting the neural capacity based on data complexity. The authors demonstrate the effectiveness of SNDS by comparing it with existing methods on 3 datasets using different querying techniques, showing significant improvements in search efficiency and final performance. The method's core innovation lies in using variational inference to learn the neural architecture depth uncertainty, enhancing the search flexibility and promoting better model performance. The limitations of traditional active learning methods are discussed, and the concept of dynamic neural depth search is introduced to address these limitations. The rich get-tricker problem in current VIBASED methods is highlighted, where shallow networks dominate the search. A new method, ActiveSense, is proposed, which continuously searches for new neural network depth distributions during the active learning process. This approach outperforms traditional AL and VIBASED methods in extensive experiments. In the realm of active learning, AL, early stages often face challenges due to overparameterized models leading to poor generalization performance with small-scale training sets. To tackle this, researchers have turned their attention to architecture optimization in AL, particularly focusing on deep neural models. Prior works, such as ActiveINAS, dynamically increase neural capacity during AL cycles, while variational inference, V-based methods are used for neural depth search, NDS. This paper diverges from these approaches by combining V to learn the neural architecture depth uncertainty, rather than increasing the basic block. Current VIBASED methods approximate the architecture depth posterior with V based on the meanfield assumption, resulting in the rich get-tricker problem. This study proposes a structured variational inference to restore the meanfield assumption, significantly enhancing search effectiveness. The authors theoretically demonstrate how the rich get-tricker problem arises from the meanfield assumption and suggest a pseudo-uniform sampling method to implement the SVI. The paper begins with an introduction to deep active learning, where a large unlabeled data pool is obtained, and a deep model is trained to sample new batches of samples for labeling. The ultimate goal of AL is to achieve higher model performance with a lower label budget. Key aspects include the model's generation performance and query effectiveness in AL. The authors also delve into statistical learning theory, which bounds the generation gap, and show that the VC dimension of the model should grow linearly with the increasing sample number of the training set. The concept of searching the optimal neural depth during active learning is introduced, where a truncated Poisson distribution is used to model the neural depth. Challenges in neural depth search include overparameterization and the impracticality of navigating the depth search through generalization performance. This research aims to address these challenges through its novel approach, offering potential advancements in the field of active learning. The paper addresses the limitations of meanfield variational inference, V-based methods in neural network depth search, specifically the rich get-tricker problem. This issue arises when shallower networks are favored due to the independence assumption between neural weights and architecture depth. To overcome this limitation, the authors propose structured variational inference, SVI, which relaxes the independence assumption and allows for customization of weights for networks with different depths. This approach enhances performance in variational inference for neural depth search. The authors illustrate the problem with meanfield V by demonstrating how it favors shallow networks, as shown in Fig. 2. They also provide an intuitive comparison between meanfield V and SVI in Fig. 3, highlighting the advantages of SVI. The proposed SVI method improves the search flexibility and final performance in neural depth search, offering a promising solution to the challenges posed by meanfield VIBASED methods. In the realm of deep neural networks, training processes are often characterized by shallow layers converging faster than deeper ones. This phenomenon leads to a higher sampling probability for these shallow layers. To better understand and address this issue, we delve into 2 key concepts: meanfield variational inference and structured variational inference. These methods involve graphical models that differ in their approach to representing complex distributions. However, they share a common limitation: the mean field assumption, which simplifies complex distributions but can lead to inaccuracies. To overcome this limitation, we introduce the pseudo-uniform sampling method. This technique allows for more accurate representations of complex distributions within our models. Building upon this, we explore the active learning with structured neural depth search technique. This algorithm operates on the principle of actively selecting samples from the dataset based on their potential to improve model accuracy. It systematically navigates through the neural network's depth, identifying and leveraging the most informative samples. The efficacy of these techniques is evaluated using three benchmark datasets: MNIST, CIFAR10, and CIFAR100. These datasets provide a comprehensive testing ground for our methods, enabling us to assess their performance in various contexts. Through this research, we aim to enhance our understanding of deep neural networks and develop more efficient training strategies that can effectively utilize all layers of the network. The active learning with structured neural depth search (ActiveSNDS) algorithm is used for searching the optimal neural network depth. It starts with an initialization of the layers and iteratively adds new layers until a maximum depth is reached. The algorithm computes the loss function and gradients for each layer, updates the parameters, and acquires new labeled data through active learning. It employs different search strategies, including mean field V and INES, and compares them with the proposed method SVI. The implementation involves the use of ResNet architectures and basic blocks with residual connections. The network architectures are emphasized in the figure provided, highlighting the differences in their search spaces and network structures. The authors present the experimental settings and results of their proposed method, SVI, for neural architecture search. In SVI, the network output is a weighted sum of the predicted output of each layer and their respective probabilities corresponding to a truncated Poisson distribution. This allows the method to avoid the performance impact of artificially limiting the search space. The experimental settings include using stochastic gradient descent with a batch size of 128, momentum of 0.9, and an initial learning rate of 0.01 with cosine rampdown. Weight decay is set to 1e4, and two data augmentation techniques are applied. The authors also provide detailed settings for depth search and active learning experiments. In the depth search experiments, the authors use all training samples of the corresponding dataset and adjust the training epoch accordingly. For active learning, three querying strategies are used: random sampling, coreset, and uncertainty entropy. The authors performed 10 active learning cycles with every candidate network being trained for 10 epochs per cycle. The datasets used are MNIST, CIFAR10, and CIFAR100. The authors provide specific settings for each dataset, including the initial number of samples, the amount of data queried per active learning cycle, and the total number of training samples. The search methods include fixed network structures, active INAS, and active SNDS. The authors train for 50 epochs per active learning cycle and use ResNet 18 and ResNet 34 as fixed architectures. For active INAS, the search space is in the range of A, bridge, 1, 1, to A, bridge, 12, 5. The results of the depth search experiments on CIFAR10 are presented in Figure 5, which shows the accuracy and probability of each layer selected by SVI and meanfield V. The authors compare the depth search results of SVI, meanfield V, and INES, as well as the performance of these three methods in ResNet 18 and ResNet 34 using all datasets on three datasets. The results show that SVI effectively alleviates the Rich-Getricker problem and searches for the optimal number of traversal layers. The authors also observe that their method has a shallower number of search layers on MNIST and a deeper number of search layers on CIFAR100, which corresponds to the actual task complexity. The table on page 8 presents depth results of various neural architectures on CIFAR10, MNIST, and CIFAR100 datasets. Mean field V and SVI achieve higher accuracy than ResNet 18 and ResNet 34. The authors also provide active learning curves for MNIST and CIFAR10 datasets using query functions like random sampling, coreset, and uncertainty entropy. The curves compare different search methods and fixed architectures, showing that INES performs poorly due to its limited search range. In contrast, mean field V and SVI excel by effectively exploring the architecture search space. The active learning curves start from an initial seed size of k equals 100 for MNIST and k equals 2000 for CIFAR tasks, demonstrating the effectiveness of different query functions and search methods, with mean field V and SVI consistently outperforming others. Active learning experiments on the CIFAR-10 dataset were conducted using various query functions, including random sampling, core set, and uncertainty entropy. The goal was to evaluate the performance of different active learning methods, specifically active SNDS and active INAS, in terms of test accuracy and depth search results. The active learning curves for the CIFAR-10 dataset using the three query strategies are presented. The results demonstrate that active SNDS consistently outperforms active INAS and other methods throughout the entire range of labeled points. Depth search results per active learning cycle on CIFAR-10 using the query strategies of random sampling, core set, and uncertainty entropy are presented in tables. The tables show the structure and depth of the network searched by active SNDS and active INAS, as well as the value of the parameter lambda d, which controls the depth in network training. The results indicate that active SNDS searches for deeper networks and achieves better performance compared to active INAS, regardless of the query strategy used. Mean field variational inference is employed to approximate the posterior distribution of the network weights, and the parameter lambda d is learned using a variational inference approach. Overall, the results suggest that active SNDS is an effective active learning method that can efficiently search for the optimal network architecture and hyperparameters, leading to improved performance on the CIFAR-10 dataset. The active SNDS method addresses the rich Gettricker problem by expanding the search space for network depth, unlike mean-field V. It starts with simple networks and increases complexity as training data grows. The MNIST and CIFAR-100 experiments show active SNDS outperforms others with fewer training data, achieving better performance and demonstrating significant improvements in deep active learning.